Good afternoon and welcome again to the Security Seminar. For our viewers who are located elsewhere than at Purdue University, particularly our viewers in other countries, I'd like to remind you that next week is a holiday here at Purdue. We will not be having classes, and therefore there will not be a security seminar. We will, however, resume with the seminar series 2 weeks from today. Today's seminar is a little bit different than previous ones. The last few seminars we've had a number of industry practitioners and a few pioneers of information security who've been involved in the field for some time. This week we're doing something a little bit different. We have two people that we expect to be very significant in the field of security in the years to come, but who are currently working as graduate students at Purdue in CERIAS. They'll be speaking one after the other on topics of research they have been involved in recently and will be presenting at an upcoming conference. Our first speaker today is Kevin Du. Kevin has been involved with CERIAS for the last few years and spent some time doing research into security of Windows NT. His talk is going to be on the security relevancy analysis of the registry of Windows NT 4.0. So our first speaker, Kevin Du. Kevin?
Thanks, Beth. My topic of this presentation is security relevance analysis on the registry of Windows NT. And let me first introduce the background of this project. And the paper is, there are two co-authors in these papers. One is the Private Guard from Microsoft Corporations. Another is Professor Martha from CS Purdue Universities. And the paper will be presented in the conference of 15th Annual Computer Security Application Conference in Arizona this December. This work has been done during my internship last year from May to November in Microsoft. I spent half years doing security analysis on Windows NT registry during my internship. And the paper is the summary of the work and some result we got out from the analysis. So first, let me give you the outline of my presentations. First of all, I don't assume that all of you know the concept of the registry in Windows NT. So I'm going to give some brief introduction on the registry concept in Windows NT. Then I will point out the problem with the registries. And the next step, we are going to analyze what is the actual problems with the registry. We are going to formalize the problems. And from that, then we'll derive our solutions to the problems. Then we'll give out the result that we produced by using the solutions. And at the end, I will conclude the presentation by giving some suggestions and comments. So what is the registry? Registry is organized storage for operating system and application data in the Windows NT operating system. So basically, it stores a lot of data that application and operating system depends on. And one example of this kind of data is like when you fire up a Windows, the background colors, this information is stored in the registry somewhere. And some other things are also stored in the registry. And some of information are very important. And one property of this registry is the data are globally shared. So for example, you have one application, you store your data in the registry, and then every other application can read from this registry if the permission is set correctly. I mean, set up to the word readable, then everybody can read the data. So it's globally shared. And one good thing about this registry is it's well organized. It's organized using a tree structures, and it's just like the structure we used in our directory structure in Unix system or Windows NT system. And let's look at an example of the registry key. And in this key, you can see the HK local machine. That's the root of this registry key. And under this root, there are a lot of different sub-registry keys, just like the subdirectories, like software, then Microsoft, Windows NT, current version. The final key is the WinLogon. That is the keys used by WinLogon component in the Windows NT operating systems. And within each keys, there are a number of values. We call it registry value. And each value consists of a name and the data. So in these examples, you can see the policy handler is the name of this registry value. And the foo.dll, that's the data from this registry value. So whenever you want to get some data from the registry, you just give the system a name of the registry key and the name of the value. Then you can get the data if you have permission. So that's the basic concept of the registry. It's a simple concept. And since a lot of important information are stored in the registry, so we have to put some protection on the registry. So the protection is like there's some ownership on the registry key. If you are owner of the key, so that means you create that keys in the registry. So you are the owner, and owner has some special permissions. And there are some other permissions which, if you are familiar with the Unix system or some other operating system, you can understand the permission of read, write, and create, and also set value, and the query permission and delete, and some other permissions. So that's our permissions to protect the registry key from unauthorized use. And when you buy a Windows NT operating system, the operating system comes out with the initial protections. And the interesting thing is some registry keys are set to be word writable. So that means you can write into these registry keys and the values. And the reason, I will give you the reason why they have these initial configurations. And also the problem with the registry comes from this. So, and I will point out exactly what the problem is. So one comment about the registry directories is a nice idea. It's well organized hierarchy structure, and you can share information. But the problem is it gets abused. Now everybody knows, oh, we have a nice storage of information here. Okay, let's use it. So there's a lot of unnecessary use which cause the problems. And from another perspective, let's look at the registry key values as global variables. And everybody here knows that when we are taking program class, we are told not to use global variable because they are not good from software engineering principle. So now the registry keys and values basically are global variables. They are not only global variables shared within the programs, they are global variables shared among different applications. That means they are global shared in large scope. So let's look at the examples how that bring up the problem. Here's a component 1, and in this component they use HKey local machine and blah blah and some component 1. Actually, this is a real example. It's not that I make up the program, the examples, but the key name I used is faked because I don't want you to attack the Windows NT using this. And inside this key, there's a value called font. The value name is called font file. So basically what that means is the data part is basically a file name. So this is like specify a font name, so probably some component want to use some font, and the source of font will come from this file. And permission is set to word writable. And from looking at these keys, and the designer of this component 1 will think, okay, this font, I will use this registry values only to like for some display some font for that purpose. So to me, this is not security relevant. I don't need to protect that. And probably that's true. Like in this component, you don't need to protect the font, protect these keys. But let's look at, then in the midst of millions of lines of code, there's another component we call it component 2. This component will be used by administrator. So which means when it gets wrong, it will have privileged permissions. And what this component does is take the file name from the registry key and do some computations, and finally decide to delete this file. And this component might be some upgrading component, which will like install a new font and delete the old one. So then the problem, here's the problem. So if the key is word writable, then everybody can modify the registry value inside that key. For example, I can let the file point to some very important files, like the password file or some other system dependent files. Then when you run the component 2, you will actually delete that file. So that's security problems. So let's look at some in an abstract way what exactly the problem is. This is a model of the component 2's behaviors. So here in the right we have a registry key, and the program will get value from this key, and the value will be installed in a variable we call fn. Then after several computations, the program come up with another variable fn prime, and it goes ahead to delete this fn prime. And we all know the delete action is a security critical action. By that we mean if you apply this action on some arbitrary like names, you will call the security breach. So that's what we mean by security critical actions. So that's basically the behaviors of the component 2. So what we are looking for is we want to know if there's any relationship between the variable fn prime and the registry key. So if we found out that the value of fn prime depends on the registry key, then we can say that k is security relevant, because the value stored in the key will affect the value of fn prime. So that means if somebody like mess up with the key, it will affect the security property of this program. So since the input is stored in a file fn, so the problem reduced to we have to find out the relationship between two variables, fn prime and fn. And we reduce that problem to a dependency analysis problems. So we want to know if fn prime depends on the variable fn. By depending, I mean if the value of fn is modified, and the fn prime, the value of fn prime will be affected. So actually we are going to find this kind of dependence relationship among the computations, because the only relationship you can derive is from the computation related to fn and fn prime. From the program, fn and fn prime you can derive any information without looking at the computation. So we reduce the problem to a dependence analysis problem. And I'm not going into the detail of this dependence analysis techniques. It's basically we didn't invent this dependence analysis. We use it from the static analysis communities. It's well studied in the static analysis communities. A dependence is basically a tuple of two variables. So look at the examples. If there's a statement, we assign variable v to the w, and we will say the tuple wv belongs to this dependence relationship, which means the w depends on v. And also look at the string concatenation. We concat the v's, the value pointed by v, to the value coined by w. So we have a star w and the star v tuple belongs to the dependence relationship, which means the value pointed by w depends on the value pointed by v. And if we can establish the dependence relationship from all the statements in the program, then we can build a data dependence graph. A data dependence graph is basically a directly graph. Each node will represent a variable, and each edge represents the dependence relationship. For example, in this graph, there's an arrow from x to y, which means y depends on x. So we will build this graph using the information we derived from the program. And also, we have an inode. We mark some node as inode, which means the variables of this node actually represent values in the registry. So, for example, if you get input from registry, you store the value to the variable w, then this w is marked as inode. And also, we have an S node. S node means it's security critical. Some security critical action has been applied on these variables. From the previous examples, the inode is actually fm prime, which was the delete action was applied on the fm prime. So now we have all this graph. We have this graph. We have inode, S node, and now we are going to derive the security relevance information from this graph. So from this graph, if there's we are going to find out if some inode is security relevant or not, because each inode represents a value from the registry key. So how do we figure this out? From the graph, if there's a path from inode to any S node, then we can say that W is security relevant. So it's as long as we have the dependence relationship, then figure out the security relevant is very straightforward. But there's some issues in this dependence analysis, and some issues are very hard, and people publish a lot of paper in this area, like areas, because of these are caused by the introduction of pointers, and also by the function calls. This is whole difficult issues, and also there's some global variables. And this makes the dependence analysis more complicated. And also, because of incomplete programs, which is introduced by the library function, because the assumption of this analysis based on that we have all the source code of the program, but you don't have source code of the library functions. So we have to do something to solve this problem. And also another difficulty is the indirect dependence. Like example, I give the if this actually there's no assignment of value v to value w, but actually the w's value depends on v. So these are hard questions, and we are not inventing any techniques on this. We just use the solutions in the literature. So let's look at how this works. This is a simple examples. So in the second lines, we we have a registry query key, and this function call will actually get some data from a registry key and store the data to the input variables. And then it will invoke G, function G. Function G will do some computation on this input and then invoke H. So H will create a process and it will run a program. The name of the program is specified by the N. So actually, the create process is the security critical actions, and we don't want that N to be arbitrary values. So in these examples, we want to know if this security critical action has anything to do with the input from the registry. So use our approach, we will derive the dependence relationship, and we will build this data dependence graph. And the node marked by I is the I node. The node by S is S node. So from this graph, we can immediately find out that there's a path from star input to the star N. And N is the security critical node. So now we find out that this input is security relevant, and which means the registry key corresponding to this input is security relevant. So let's look at some result we generate from using this approach. We start to focus on 50 registry keys because of time limitation. They have 16,000 keys. That's a lot. And 21 of them are security relevant from our result. And among these 21 keys, 11 are word writables. So that means if our approach, our method is correct, this 11 key could be exploited to break the systems in some way. And some interesting things among these 11 keys is some are unknown before. That's good, because that proves that this approach is valuable. We found something that is unknown. And to my surprise, some are known to be security relevant, but nobody knows the reason why they are security relevant. So probably it's inside of some documentation they said, oh, we should protect this key. Then they protect it. They have documentation say, okay, we have to protect. But after from NT4 to from NT 3.5 or to 4 or to some version, then they got lost of this, like the reason. They don't know exactly why we need to protect this. So this result gives them the reason that this is why we need to protect them, because somebody is using this in a very security critical actions. And then one comment about this is, why not just protect all of the registry key? That's the first question I ask them when I start to work on this project. I ask them, why not just protect all the keys so I can enjoy my internship without doing anything? So that's something that I learned from my internship. They said we can't, because we are dealing with some legacy code, and some of code are developed in the Windows NT and for the Windows 95 and for the 98. Of course, they're also working in the NT, and considering that in the 95 and 98 there's no such protection as NT does. So programs will tend to make this kind of assumption, because they don't have concept. There's no concept of protection on the registry in those operating systems. So there's many programs made assumption that this key is word writable. Somebody can write on these keys. So if you secure them, some application will not work. And if you want to like modify them, and some application has to change their design. So that's not things they want. So if they want to figure out exactly which keys are security relevant, then they will put that as high priority to secure, but not all of them. So then here's my conclusions. The first is knowing security relevance of registry key is important. And the second, we have developed a method to conduct security relevance analysis on Windows NT 4.0. And if they are interested in this, they might like use this approach in the Windows NT 5.0. And the result are proved to be useful at least from them. And I will end this presentation with some suggestions. So the first suggestions from user perspective. So you do not assume too much. You don't assume that the registry key is protected. You don't assume that the information stored in the registry key is consistent with the real situation. I mean, with the system behavior. And also we know that using global variable is not good. So we need to avoid unnecessary sharing among the keys. And from the anti-registry perspective, and that's one suggestion I made to them before I left Microsoft. And the first thing is we need to put some more control on the usage of the registry. The problem we have right now is we don't have a global view of the whole usage of the registry. If somebody is using registry key in somewhere silently, nobody will know that if you don't look at their source code. So we have to put some control on that. So if you want to use this, you probably use some registry mechanism. If you want to do this, you have to tell some central place, okay, I'm doing this, and then we have a global view on that. And another thing is we might like use some mechanism to limit the scope of sharing. Not like this. Let every application use this. Perhaps some more limit, some limit could be useful. So this will end my presentation. So if you have any question, please ask.
I have two questions. Mm-hmm. The first is a clarification. How is the S node chosen?
Oh, that's based on that's from the heuristic. This not automatically. You look at some things, you immediately know this is security critical. So you have to look at all of the system calls and say, you decide that this is security critical, this is not. That's the way we did it, yeah.
And the second question is, let's forget about those intricate dependencies. Mm-hmm. You said it's a hard problem, right? Mm-hmm. But you gave us two examples of direct dependencies, functions, mm-hmm. or methods. One mm-hmm. was assignment, the other was some string concatenation. Mm-hmm. Mm-hmm. Which of those functions do we know should be used to decide that there is a dependency between, say, W and B?
No, you look at all the statement, then you derive we have some rules. So if you have this statement, assignment statement, what you can derive for the dependence relationship.
Yeah, but my issue is I want to know if I should draw and add an edge to the graph. Mm-hmm. Right? Let's say that some function is being used, say addition. Yeah. Plus of W and V and mm-hmm. being assigned to W. Mm-hmm. How do I decide whether the plus is security relevant enough that an edge should be added to the graph?
No, you're not deciding on the dependence or relationship based on some security things. That's the way you decide if this variable is dependent on another value. It has nothing to do with security. It's just from the structure. Okay, this assignment from this assignment, we know the variable at the right side, at the left side, depends on the variable in the right side. So it's nothing to do with security. Yeah.
So how long did this analysis take for the 50 keys that you looked at?
It takes because the problem is there's some, as I introduced, there's some hard issues. So in some place we have to manually do something. So that add up to the cost. We are trying to solve this problem, like make it totally, completely automatic. Then that we like make it faster. But right now, for this total 50 keys, and I spent like 2 weeks to look at them and then come up with this result. So yeah, if we cannot solve those like manually problem, then this is not scalable. We have to do something on that. Yeah, that's true.
Other questions? Thank you, Kevin.
Thank you.
Well, if we generalize from Kevin's results, then that means that a typical installation of Windows has 3,500 vulnerable keys, and that should keep people busy for a little bit of a while, and perhaps lay some groundwork for our next speaker, Mahesh Tripunitara has been working on how to thwart denial of service attacks against communication protocols, and he will be telling us about the results of his research. Mahesh?
Thank you. So that's my name, and I know it's a fairly long and convoluted title, but the key phrases from that are denial of service in communication protocols, and we have an interesting and useful design constraint called backward compatibility. So that's what the phrase backward compatible refers to. And so that's my name, Mahesh, and I implemented this and performed the initial work at AT&T Labs, and Partha was my manager there, and Clay Shields is faculty here with whom I have been pursuing this further, and I will mention the work I've been doing since I left AT&T. All right, so let me jump to the example. If you remember in the title, it said a case study. So I'm going to give you an example, solve the problem in the example, and then make comments about the general, any generalizations we can make about the problem and the solution. The example pertains to the address resolution protocol. So let me just tell you briefly what the protocol is about, and I think it's best explained using the standard issue TCP/IP protocol stack. So we have an application, and the application uses TCP or UDP to communicate. But an application typically likes to use domain names rather than IP addresses, right? So there is a distributed database on the site called the DNS that it consults, and the DNS in turn uses TCP and UDP to make its resolutions. Similarly, when IP wants to communicate over an Ethernet local area network, in the local area network, IP addresses make no sense. One has to use Ethernet addresses. So there's a protocol sort of to the side called the address resolution protocol that's used to map IP addresses to Ethernet addresses. And one can assume, at least for the sake of this presentation, and most other cases, that the mapping between an IP address and an Ethernet address is one-to-one. That means given an IP address in a LAN, there's exactly one Ethernet address corresponding to it, and vice versa. So that's the address resolution protocol. It's a very simple protocol. The types of ARP frames one can have are request, response. There's a couple of other special cases, but I'll make comments about them later. We don't have to worry about them. And here's how it works. Let's say host A wants to send IP packets to B on the same local area network, of course. A sends out a request for B's Ethernet address, and this request is sent out to all the hosts in the local area network. in other words, is broadcast, because A doesn't know where, what B's Ethernet address is. Presumably B responds with an ARP response packet and says, my Ethernet address is something. And A maintains a cache of these addresses. This is primarily for performance reasons, because if you have a TCP session, say, we don't want ARP requests going out every 2 seconds. In fact, the typical timeout for an entry in the ARP cache is in minutes, say 20 minutes, something like that. Again, there are some special cases such as proxy ARP, where B does not have to respond but has a proxy that responds for it. There is something else called gratuitous ARP, which is used, for instance, in the dynamic host configuration protocol to check if 2 machines are using the same IP address. This is a typical case of on the internet, when we have something useful, we try to build things on top of it without necessarily thinking about the security consequences. Anyway, so the ARP cache at each host, it's populated by mappings made from ARP requests. But according to the original RFC that discusses ARP, a host is required to also maintain in its cache mappings derived from unsolicited responses. What that means is, let's say host A receives an ARP response from B for no reason whatsoever. B just felt he was in a good mood and sent out an ARP response. And A is obligated to cache it. Similarly, if say host C sends out an ARP request and it broadcasts this request to everyone in the local area network, turns out that the mapping request, IP address and Ethernet address of C are in the request. And A will, in a good-natured manner, cache that. All these are optimizations built into ARP, because the original goal of ARP was to keep it lightweight, super optimized, so that it doesn't come in the way of performance of, say, TCP. So here's how an attacker could use the address resolution protocol to attack IP. The attacker could send a bogus request and say, well, in the source IP and Ethernet address fields of request, he or she puts in somebody else's IP address. So in other words, now a host A that receives the request and caches the mapping information will believe that the attacker's Ethernet address maps to some other legitimate host IP address. Or an attacker could send an unsolicited response which has bad information in it. Or the attacker could wait for a request to be generated by host A and then respond. But if the legitimate host also responds, then we have a race condition. But this is an interesting race condition where the tortoise in fact beats the hare, because the response that arrives later has precedence. So it's a kind of a weird, it's a slow race. Anyway, that's how ARP can be used. It's very straightforward, very simple. The protocol has been around for, 20 years, and these problems have been around for 20 years also, since the protocol. Nobody has proposed a good solution to it until now, of course. Here's some design constraints for a solution. I mean, if one looks at the problem, one says, oh, this is so similar to DNS. In DNS we have the same issues. If a machine makes a DNS request, an attacker could not just send the response to that request, but also try to help out the host, so to speak, by sending a bunch of junk along with it, and the host happily caches it. There's a lot of similarities, understandably. So why don't we just dismiss this as a standard issue security problem? I will make comments about that in a very short while. But let me just tell you the design constraints that were imposed upon me when I had to devise a solution. The most crucial design constraint in a solution is the need for backward compatibility. This means, suppose I choose to design a new version of the address resolution protocol to fix these problems. Then the new version must interoperate with the old version. And the reason this design constraint was imposed was, it was not just to make the problem harder for me, but it's because at AT&T, at least the division I was in, a network middleware was being developed where one could not assume that all hosts in a local area network were under the control of AT&T. AT&T is just a network service provider. So that means a standard issue client must be able to interoperate with the network middleware. And there's actually more interesting reasons behind backward compatibility. If one looks at, say, IPsec, IPsec is not backward compatible with IP. And there is tremendous inertia on the internet to adopt new versions of protocols, even if there is a belief that these new versions will give considerable advantages. IPsec has been around for 5 years, and people are still arguing about whether it's good, it's bad. And we even have somebody of the stature of Vint and Cerf going out in public and appealing that IP version 6 be adopted. But hey, there's tremendous inertia in adopting new versions of protocols. But on the other hand, you see that technologies such as firewalls and network address translation find easy adoption. That's because they're backward compatible. IPv4, nothing changes. So there is a compelling reason to adopt backward compatibility as a design constraint in designing security solutions. The other constraints were primarily implementation related. One of them was that the implementation had to be implemented as, it had to be middleware, meaning, you know, insert some components here and there, but don't change anything that exists. Don't, because we don't have access to operating system source code. You know, maybe the machine is running on, say, a Solaris machine, you know, and this is AT&T. They don't have access to Solaris source code. They don't want to have access to it because then maintenance becomes an issue, and so on. And the last design constraint was asynchronicity, meaning a solution that involves checking something or doing something every X units of time is not very desirable. The reason is we then end up with the problem of deciding what is the ideal X units of time, which is a nasty problem. So it would be preferable if the solution was asynchronous. And the setting for the implementation was a streams-based networking subsystem, which is what is used in, say, Solaris. And the streams is actually a very good, that's a subjective comment, model for building networking systems because it's modularized. There's something called streams modules and things like that that can be inserted. So let me give you, here's the solution. And I'm just going to tell you broadly what the solution is. And the reason is I want to make more interesting comments that are not in the conference version of the paper, but we are working on a more beefed up version right now which addresses more interesting questions. So again, we are still talking about the case study, the example, like I said. So here's a solution to the ARP cache poisoning problem. Ignore responses from the host because they don't affect the ARP cache. So the host means the host in which we want to incorporate the solution. So this is the host whose ARP cache will be protected from being poisoned. None of the other hosts in the local area network will even know what is happening. You know, they just continue to use ARP and IP and so on, unaware that a certain host is protecting itself. So in terms of responses emanating from this host, we need to do nothing. As for requests or unsolicited responses that are received by the host, just don't map the information from them. You know, honor the request with a response, sure. If an unsolicited response is received, just ignore it. Simple as that. So that's a policy decision. But, well, Bob Blakely from IBM says if you have to use the word policy in any solution, in any security solution as a parameter, then you've done something wrong. Go and redesign your solution. So I'm not using policy as a parameter. I'm just imposing a policy decision in my architecture, saying ignore requests and responses. Because if a host A wants to transmit IP packets, then it will reflect that desire by sending out an ARP request. There is no need for us to add this little optimization. Of course, the proof of the cake is then in the eating, and I'll make some comments about performance of our solution at the end. Lastly, we have to address the issue of a request being sent out by the host that we are protecting. When a request is sent out, we record it. And then when responses are received, we try to match them with the request. So there's actually more to this than meets the eye. What if 2 responses are received? What happens? The interesting thing here is we don't care to identify an attacker. That's because we don't even know who the attacker is. For instance, let me give you a situation in which there is no attacker. Let's say that we are running DHCP. We had the RAID conference here where there were 200 people here. Everybody was plugging in their laptops, checking email, shutting down, leaving, and then somebody else would come and take over the port. Let's say a machine has an IP and Ethernet address assigned to it, and then that machine goes down, and another machine takes over that IP address, but it has a different Ethernet address. That's perfectly okay. There's nothing wrong with that. It doesn't mean that the second machine is an attacker. So we need to be able to address these types of nuances in the address resolution protocol. So perhaps you're not convinced that this works because it's so simple, and I'm just about to make comments about that. At least the program committee and the reviewers of the conference bought it. So okay, so now I'd like to move on to stuff that is, if you want any details on the implementation, which are all gory details about streams, if you want to understand streams, I can give you the 600-page manual that I had to suffer through to understand it. But there is really nothing much of interest in there. The crux, I think, is in these sorts of questions. The first question is, well, at the start, I never told you what denial of service means. That's because I don't know. And I wonder how many people in this world do. But in any case, we have some sort of sense for what denial of service means. It means an authorized principal wants to have access to resources or data, and it's being denied that. Why is this a denial of service problem? Because as far as we could see, this seems more like an authentication problem or something. I mean, there is no checking going on of who is sending what type of information, right? So it's not clear that people have argued with me in the past about why I had called this a denial of service problem. The second question one could ask is, why not just recast this as an authentication problem? So this is related to the first question, right? And the third question is this just an ad hoc solution? Meaning I presented you a problem and I say, okay, here's a solution. I mean, is that it? Suppose someone presents me with a new denial of service problem. Will I have to redesign and come up with a new solution? Is there anything more general that we can draw from this solution, from this approach? So let me try to answer those questions. Why is this denial of service? Well, because this is denial of service on IP. If an attacker carries out any of those three attacks that I listed, a host A, supposing it wants to send IP packets to host B, those packets never get there. Therefore, it's denial of service on IP. So one might choose to characterize this as a problem in the address resolution protocol, but the consequence is denial of service on IP. The other reason it is reasonable to characterize this as a denial of service problem is motivated from the solution standpoint, which is when Don Parker was here, he told me that there is a tendency in information security professionals to resort to the standard issue sort of approaches to designing solutions in information security, which is authentication, authorization, access control, this type of thing. And he said one approach or strategy to solve security problems that's neglected is avoidance. Pass the buck. If you can't solve the problem in some context, try to solve it in another one, but yet solve the problem. That's exactly what we are doing here. We are not fixing ARP. With the solution, the same problems exist with ARP. It is, it's bad, people can still do all kinds of nasty things. But what we've done is we have passed the buck to IP, so to speak, or at least we have fixed the denial of service problem, not that we've changed IP. So that is the perspective behind which, based on which I think it's okay to characterize this as a denial of service problem. The next question I listed was, why not recast this as an authentication problem? Isn't that what it is? ARP messages have no proof of origin, for instance, who this comes from, and so forth. The first response I have to that is that authentication is sufficient to solve the problem, but it's not necessary. So what that means is we go to the second point, which is that authentication solutions, I mean, we are told that, for instance, hashing with the secure hash algorithm is lightning fast. It's very fast, it's not an efficiency issue. But let's take ARP again as an example. An ARP message is maybe 40, 50 bytes. The secure hash algorithm, a hash is 160 bits, which is 20 bytes. Right? That's 40% overhead, just in some terms of the data, if I want to attach a digital signature based on SHA. The second thing is, I mean, the standard issue authentication solutions are based on public key cryptography, and then we exchange some secret keys. I mean, the key management is a major issue, right? I mean, this is not a simple thing. And ARP was intended to be a lightweight protocol. Even TCP, I mean, if you think about denial of service attacks involving TCP, think about TCP connection establishment. It is so easy. I mean, it's just 3 simple messages back and forth. If you're going to sit, if we want to, if we incorporate all these keys and things like that, I think it's pretty heavy duty. And of course, key revocation. I mean, there's a huge problem right there. So that's why authentication, that's one of the reasons authentication is very unappealing. There's another subtle problem with recasting this as an authentication problem. And that is, when we say authentication, what we mean is authenticating the origin of a message. So in the case of the address resolution protocol, for instance, what we are saying is to solve the problems in the address resolution protocol in an authentication type of setting means we trust some hosts to always speak the truth. In which case, all we have to do is ensure that data packets are coming from this host. In which case, we would just trust only packets coming from this host. And using authentication, we can verify beyond any doubt that the packets are indeed from these trusted hosts. But that is not really the issue here. The issue here is we want to be able to verify the contents of the packets. And this is not a problem that's specific to ARP. It exists, for instance, in routing updates. Let's say you have 2 routers of 2 companies that are competitors. Let me pick 2 fictitious names, Sun and Microsoft. Let's say their routers are connected to each other. And Sun's router receives a routing update message from Microsoft's router, which essentially implies, I'm the best way to get to Sweden. Send all your packets to Sweden, send it through me. The Sun's router might be able to verify beyond any doubt that indeed this message comes from the Microsoft router. But that doesn't necessarily help. What Sun's router wants to make sure is this router speaking the truth when it says that it is the best way to get to Sweden? So that's a much harder problem. And I think we can bury the problem under authentication, but it doesn't solve it. The last question I asked is this solution ad hoc? And the answer is no. It turns out that this solution satisfies something called the fail-stop property, thanks to Schneider, who first proposed it in '84 in a completely different context, which is fault tolerance in processors. Lee Gong and Paul Syverson sort of brought it back from the dead very recently and suggested that it could be useful in information security as a weaker form of security than the strong authentication techniques we are familiar with. And then most recently, Catherine Meadows, who spoke a few weeks ago here at the security seminar, suggested that this could be used in the context of denial of service. The only problem I have with what Meadows spoke about and the paper that she published is that she again chooses to recast denial of service as an authentication problem. If you read the paper or if you attended the talk, you might have noticed. The second thing, of course, is that she focuses on cryptographic protocols and not protocols used on the internet such as ARP and TCP. Oh, by the way, there's one other problem with viewing recasting denial of service as an authentication problem. The solutions we are familiar with for for authentication are not backward compatible. You would have to change the entire protocol. Anyway, so solution is not ad hoc. The fail-stop property helps us. And what we have is, and I can give you a preprint of the paper I'm writing right now on this, there's a theorem in there which proves that indeed the new version of ARP that I'm proposing provides provable resistance to the denial of service problems that we just discussed. And yet we have a backward compatible solution. So we have the best of both worlds. So right now, this is my last overhead slide. We have a formal model and description of the protocol within that model. We have proofs for the security, which is using the fail-stop property, and we have performance measurements. I do have some perfunctory performance measurements already for my implementation, and it shows that the impact is 4%. Of course, I'll have to tell you more details of the tests I used, but the impact seems to be okay. We are currently looking at applying this methodology to other protocols from the internet, notably TCP, I just threw the others in there to show you that we have been thinking about it. But in the end, sort of the broad question is a better understanding of denial of service. Thank you.
Could you elaborate a little bit more about the actual solution? You said that you compare incoming
Yes.
requests that you made. I didn't quite understand how that...
So when the host sends out a request, we record that. Okay, a request was sent out for this particular IP address. And then when we get a response, we check if there was a request outstanding. If there was no request outstanding, then we know it's an unsolicited response, so we can throw it away. If there was one outstanding, we just say, okay, and we add this to the cache. But again, we don't forget that the request was made. Now the question is a second response received to that request? So, we assume that an attacker cannot choke the legitimate machine from responding, which is okay, because it's very hard to choke a machine from responding on, at least on an Ethernet. Secondly, if the legitimate machine went offline, then that person, the one that responded, is not an attacker anymore. It's perfectly okay for him to take on the IP address. That's the essence. I can give you more details. We've drawn a deterministic colored pattern net to describe this new version of the protocol, and I didn't want to go into the details of it.
So if you get two responses, you still discard the...
No, actually in that case what we do is we just raise an alarm, because we don't know which one the attacker is, assuming they are inconsistent responses. So we just throw up our hands and say there is a problem here. But at least we have both the IP addresses and the Ethernet addresses that responded. All right, well, we have the IP address and both the Ethernet addresses. So then from then on, it depends on how we want to handle that security incident, so to speak. But the point is the host A, which we are protecting, will not send IP packets to that IP address anymore. And that's what the fail-stop property refers to. If somebody, if the instance of if the protocol run pertains to an attack, we don't want to expend resources sending.
So you basically still have a denial of service?
No, the instance of the protocol is bogus anyway. So we don't want to expend effort sending those IP packets to a black hole or to the wrong host. So there is no denial of service. And that's what the fail-stop property refers to. So if two responses are received to a request, there is a problem, and the host will not send IP packets to that IP address. We need to invoke some kind of incident handling at that point. Yeah?
Yeah. ARP, isn't it a block? It has to hold on to any ARP requests that are not valid time period of 10 minutes. Are they going to alleviate that time frame or down, keeping on cache?
Actually, it was hard for me to understand. So if there is a response, we should hold on to it for.
Doesn't the cache it has to hold on to any ARP requests that are not valid for a time frame of 10 minutes, and if they hold on for that 10 minutes, it's going to fill the cache. Yes or no?
No, I still don't understand. So a host sends out a request, and let's say it gets a response. Are you telling me that it will be cached?
It's an invalid ARP request from a host.
Oh, invalid request. No, in that case we don't cache that at all in the solution.
Okay, so you're not going to have any timeouts or whatsoever?
No, it's just the mapping just won't be cached. The request will be serviced, meaning if the request is for the mapping information of this host, then it will send a response. But the mapping information about the host that sent the request will not be cached.
Other questions? Well, thank you very much. And again, for those of you who joined us late, next week is a holiday here at Purdue. We will not have the security seminar next week. We'll resume 2 weeks from today. For those of you in the U.S., have a wonderful Thanksgiving, and we'll see you in 2 weeks. Thank you.